So binary variables, problems with binary variables are harder to solve. However, binary variables are very useful in different kinds of modeling possible. They allow us different kind of modeling possibilities. Let's look at some of them. So let us take the example of the General Wheels company, which is considering 6 large capital investment possibilities. These investments will give them different long-run profits, which have been given in net present value terms. The capital required for any of these 6 projects is also known. So what we have then is that project A, B, C, D, and F will require 38, 33, 39, 45, 23, and 27 units of capital respectively for doing the project. And estimated NPV for the 6 projects is also known to us. It's 15, 12, 16, 18, 9, and 11 for the 6 projects respectively. Now, the total capital that is available to us is 100 million. So these are numbers in millions, and let's say then the total capital available is 100 million. Now, the question that we would like answered is which investment should we select such that the total NPV is maximized? So what kind of decision variables do we need to introduce? Well, we are asking for a yes-no decision. We are saying, should we take project A or not? Should we take project B or not? And so on for all the 6 projects. So since this is a yes-no decision, it's a binary variable that we need for each one of these decisions. So therefore, let's define then yi to be a variable which will take a value of 1 if investment I is taken. I, of course, is from 1 to 6 for the 6 options. And yi will take a value of 0 otherwise. The objective is to maximize total NPV, which would then be 15y1 plus 12y2 plus 16y3 plus 18y4 plus 9y5 plus 11y6. How about the constraints? Well, we just have one constraint over here, which is the budget constraint. So the total amount of money we will end up spending would be 38y1 plus 33y2 plus 39y3 plus 45y4 plus 23y5 plus 27y6. And that has to be less than or equal to the money we have, which is 100 units. Do note that these yi variables will take only 0 and 1 or 1 values, and therefore this constraint works. So for example, if you did take up project number 1 or investment number 1, then y1 will take a value of 1, and therefore the cost for that project 38 will be applied. However, if you didn't take project 1, then yi would have been 0, and the cost for that project would then not be included in what you are spending. So it works because we have binary values for these variables. Question: investment 4 yields the highest NPV, so should we definitely choose it? Well, not necessarily. It will depend on how much you end up spending or how much capital you end up consuming in taking that particular project. In this single constraint problem, actually, this is called a knapsack problem, one could do something like take the ratio of what you are getting out of a project and what you are investing in the project. So 15 by 38, for example, can be compared with 12 by 33 and 16 by 39, etc. And then we could sort of rank these projects that way and then start picking them. But that may not necessarily include then project 4. Also, if you had other constraints, then we cannot do it this way. We will solve the general formulation with that one constraint that we have. And I'll let you do that. I have given you the template. The solution that you should get if you do not impose integer restrictions says that don't take project A, don't take project B, take project C, and then take 0.756 units of project D, and nothing of E and 1 unit of F. So the C and the F make sense. The A, B, and E you're not taking, that makes sense. But the project D being 0.756 doesn't make sense, because then that would mean that we have applied 0.756 of the cost of this project, which is meaningless. You would either have to take the entire project or not take it. We can't really round that up to 1 either, because then we will fall short of capital. So with this, the net present value comes out to be 40.6, but it is not a solution that is valid. So therefore, impose the integer restrictions, the binary variable restrictions, and then solve again and see what you get. And this is what you should get. You will be taking project A, project C, and project E. Those are the ones which are taking now a value of 1, while B, D, and F are now taking a value of 0. So those are the projects that you don't take. Very different solution from what we saw earlier without the binary restriction. And with this, then, we are saying the total net present value, maximized net present value, is 40. You've ended up using all your capital. The used up amount is 100, which is exactly equal to what was available. So the numbers are such that added up to 100. It doesn't always have to. It could have been less than 100 and satisfied that constraint.